Good morning, everyone. I'm honored to have the chance to address you on this special occasion. My name is Zerui from Beijing University of Technology. And the topic of my paper is detection of HVDC interference on pipeline based on convolutional neural network. Oil and gas pipelines are the medium used to transport oil and gas over long distance. They are buried deep in the ground and can be damaged from a variety of factors, especially the HVDC interference. The HVDC is called high voltage direct current transmission line. It refers to the interference caused by the current released into the soil during the operations of the high voltage transmission system. The duration of such interference is short, but the soil potential change is very obvious, which will cause great damage to the pipeline. In this paper, based on the time series data generated by the smart test pair, we use one-dimensional convolutional neural network to detect the HVDC interference. The data in this study were taken from the real-time cathodic protection monitors of an oil and gas pipeline system. The data was obtained by the smart test pair for cathodic protection. In order to detect the health condition of the pipeline in real time, a large number of smart test pairs are buried along the oil and gas pipeline, which are used to detect the potential current and the insulation performance of the pipeline. Each test pair is equipped with a wireless communication chip, which can transmit data to the server in real time through the Internet of Things. And then the server will analyze the transmitted data using machine and manual methods to find the possible interference problems in the pipeline. The collected data, including pipeline potential, soil environment, pipeline current, among them, the power on potential and the power off potential of the pipeline are sensitive to HVDC interference. So we use these two values as the main data source for detection. These two figures is the typical curves of the pipe potential. Figure 1 is the potential after the interference of HVDC. Point A represents the beginning of the interference. C represents the peak, and B represents the end of the interference. Figure 2 is the potential curve without HVDC interference. This table is the sample size we used. In order to realize the effective analysis of the data, we first clean the data and manually delete the obvious wrong data. These data are usually distributed discretely within the time range and have significant difference with the surrounding moments. In addition, the test pair may send the data repeatedly to the remote server, and we delete the duplicated data. The data were marked by professionals in the way that potential curve presented by the device was significantly offset. If HVDC interference occurred during a certain period of time, the data for this time range is labeled as characteristic data. In order to use the convolutional neural network to extract the features of the data is segmented. Usually, the discharge time of HVDC transmission line is about 30 minutes to 4 hours, and the data is collected every 10 minutes. We used a random way to divide the time segments. Starting from the first data after 0 o'clock every day, every L data is divided into a time segment until the data of the day is clipped. The criteria is if the segment contains HVDC data, the segment will be marked as a positive sample. Otherwise, it will be marked as a negative sample. Finally, the data was artificially checked to eliminate the segments marked with obvious errors. According to different L, we can get different sample numbers. Here is the structure of one-dimension convolutional neural network. The input feature vectors is the data to be analyzed. Convolution layers is used to extract the local regional characteristics of input vector. After multi-tap convolutional operations and the polling operations, the feature map is transformed into feature vector by flattening or global polling. Multiple folding connected layers are used to further extract a feature. The final output vector represents the result of the classification. Due to the small dimension of the data to be classified, appropriate convolutional kernel and the layer number should be taken into consideration. When designing convolutional neural network, a convolutional kernel of length 3 is used as the basic structure of the network. After every two convolutional kernels, the max polling layer is added. The number of layers of the network is increased according to the length of the input sequence. In order to utilize the extracted features as much as possible, the feature map is transformed into a one-dimensional feature vector by using flattening operation. In order to improve the speed of the convergence, ReLU is used as an activation function in each layer. Here is the experimental result. There are two groups of potential data: power off potential and power on potential and power off potential. It can be found from the result that the performance of the model on the power off potential is better than that on the power on potential, because the power on potential is affected by the potential current, and the characteristics of HVDC are relatively weakened. When L is considered, the best result of the experiment is when L is selected as 40. This is in line with our expectation, because as the length of the segment increase, the more data L contains, the more complete the segment containing HVDC data will be. When L exceeds 40, the accuracy rate drops. It may be due to the decrease of data size. Secondly, we compare the one-dimensional convolutional neural network with other classifier models. DTW and wavelet transform are common feature extraction methods in time series data classification. We choose segments with L equals 40 and use different classification methods to extract and classify the potential data. The results of the comparison are shown in the table. The experiment shows that one-dimensional convolutional neural network has better performance than DTW and the wavelet transform. This indicates that convolutional neural network can be selected as the HVDC interference detection method. In this paper, we built a one-dimensional convolutional neural network to classify HVDC, prove that one-dimensional neural network can be used to detect the pipeline potential timing series data. Power off potential data can be more easily captured as a feature of HVDC. However, the current detection method is based on time sequence segments, and its sensitivity to time is not high enough. In the future, we will develop methods to achieve more accurate detection of HVDC. That's all. Thank you for your listening.